Hello guys and welcome again. Today we'll be talking about pile caps design. So let's jump straight into it. Pile caps are quite deep elements in the sense that they don't really exhibit flexural behavior. So you'll see in the codes that when you're designing elements there is always a ratio between the span of the element and its depth. If this ratio exceeds a certain value, then that means that it's a flexural behavior because you've got a long span compared to your depth of the element. So what happens in this case is that your element is going to bend. But if this ratio is really short, imagine having a very deep beam and your span is quite short but is carrying a significant load. In this case, your span to depth ratio is quite small and your beam is not really going to exhibit flexural behavior in the sense that it's going to be bending. Instead, the structure, especially the concrete, is going to redistribute the stresses internally through compression and tension in the element. And this is what is usually solved using Strut type models. Pile caps are one example of this type of elements in the building. Because they are usually quite deep, they often need to be designed as deep beams and deep elements instead of flexural elements. And by the way, if you don't know why pile caps are quite deep, the reason is basically to get your reinforcement developed between your piles into the pile cap, and if you have a column above, to develop the reinforcement from the column into the pile cap. So they essentially act as a transition zone to develop your bars from the column and your bars from the pile. But that's not everything that they do. They also act to transfer the load from one location into a number of piles. For example, if you have a 2-pile group with a column, they act as a deep beams to transfer the load from the column into the 2 piles. Also, if you have a single pile, there's another purpose for a pile cap. It's not just to develop the bars. And that purpose is that piles often go out of location because of surveying problems or because of problems during piling. You might end up with a pile actually out of position by as much as 75 mil. And because of this eccentricity tolerances in the piling, you will still need to keep your column at the same location, but because now you have load eccentricity, it needs to be resisted and transferred between the column and the pile. And that is the purpose of having a pile cap, to transition this load from the column position into the pile position. So let's start looking at our single pile cap. We already explored the design theory behind it, that the first design rule for designing a single pile cap is to get sufficient depth to actually develop your bars. Whether you have tension, you need the full tension development length, or whether it's in compression, you need a full compression development length. If you're going to cog your bars, then you only need half of that. And then the second design is to take the eccentricity due to tolerance and piling. And for that, we're going to jump in and start looking at a strut and tie model for a single pile cap. So in the case where our pile gets actually mislocated by 75 mil, in this case we have an eccentricity. So we have our load coming from the column with a 75 mil eccentricity. And because of that, the load needs to go back to its support. So it forms a compression field or a compression strut through the pile cap. And because it forms this compression, it's actually coming out of center. It needs to be balanced internally. So we'll need an internal tie at the top. Just think about it as a truss, but it's actually hidden within the concrete element. So this tie at the top is stabilizing the strut so it doesn't go anywhere. And basically, if you just use equilibrium principles, because internally the stresses and forces must balance out in the member, since we have a compression here, that means we need to have a compression here, and then it gets balanced out by the tie force at the top. Now, one important thing to consider here is these are referred to as nodes. Nodes are basically the points of intersection between your struts and ties. And these nodes are basically points of high stress that you will need to check for bearing, and for stress nodes. But this is a bit too detailed, and we'll cover it in another section using strut and tie design and jumping into that in more detail. What I would like to mention here, because it's really important, that your tie needs to be extended beyond the node sufficiently to develop the bar in tension. Basically, if your bar is not long enough to be developed beyond the node, it cannot act as a tie. It's just not activated. It will just slide and slip out. So it's important to work out where your node is, which is usually governed by the external loads and by your internal arrangement of the strut and ties. And by the way, you can create anything. Even if it's not logical, you can still create it as long as you work out the forces internally, although it's not recommended to be not logical, but you can do whatever you want as long as you can justify it. Another thing that's important to consider here is the geometry, because the geometry is important in working out your forces, just like how the geometry of a truss is really important. So to work out this angle and resolve your forces internally for the tie member and for the compression member, you'd actually need to work out how much is the depth from the tie to actually the node at the bottom over here. Generally, if you have a 50 mil cover at the top, then that is where your tie reinforcement going to be located. So you already know this distance, and at the bottom you can take about 50 mil to where the center of the node will be, just roughly, and that would be sufficient. So your center from the tie to the center of the node here is actually gonna be this depth from your tie to the bottom, and you take out a 50 mil, and we're gonna call this Z just for the ease of reference. And the reason we took a 50 mil is because if we actually sketch what's happening over here, we're gonna have a pile, and then we're gonna have a flat surface at the bottom of the pile cap. And what happens here is that you have the compression force coming in, but first you're gonna need to have a face of this node and a face of this node, and you're actually gonna have a stress field, which we are drawing with a dashed line over here, and this stress field needs sufficient distance to actually get back and align at this point over here. So what we're looking at the center of the node, we're just taking it at the face over here. You can work out this distance in great detail once you know what is your width of your strut, but you don't need to overcomplicate things because it's within 25 to 50 mil. If you want to overcomplicate things, that's fine, it's up to you. But if you're just designing it, and as always with structural engineering, if it's there within 3 to 5%, you know it's safe and it's generally going to work. So don't overcomplicate things over here. So with the geometry, we got our distance between the strut and between the tie, which is this angle over here, theta. Once we know what is our angle, we can work it out like what we've said just now, and we can find out our angle. With this angle, we can resolve to find our compression force in the strut. And once we know what is the compression force, we can actually do our strut's capacity checks, which we're gonna go to in a minute. We can work out our tie force at the top, and with this tie force, we can straight away work out how much is the reinforcement that we need to put in that location at the top of a single pile cap. Just using safety factor times your area of steel times by the yield, that will give you how much the steel force that you have in, that should be greater than the required tie force based on your strut and tie model. And then the last thing is this eccentricity externally between the column and the pile. You gotta make sure that you specify this moment on the pile, because at the end of the day, what we're really doing is we're saying we have a point here, we have a point here, and somehow the loads gets transferred through the pile cap. So at the end of the day, if you really think about it, this one here needs to be fixed, and there needs to be a moment, and basically this moment is the load of the columns times by the eccentricity, which is the allowable tolerance is about 75 mil for piling. So you need to make sure that you specify this moment for your pile, and you can check your pile design as a column with a moment and with a compression load, and then you can design how much is the reinforcement that you're going to put in your pile. So a question that's on your mind is, how can we check the strut capacity? And the strut capacity is fairly straightforward to check. So this check that we're doing is to AS3600. You've got a phi factor, you've got your phi safety factor, you've got 0.9, and if you already don't know that, 0.9 is usually the approximation from the plastic stress that the concrete exhibit to the perfect rectangular stress that we assume, if you remember that. So whenever you're designing concrete and compression, you should always take 0.9 of FC dash because of that. And then your AC is your area of concrete, which is basically the width of the strut in two directions. So let's touch on that a little bit. We've spoken about how we split our struts something like this, and basically we can approximate that this distance is approximately equal to half of the pile size. So the area of our strut here, which is somewhat circular, is actually approximately half of the pile cross-sectional area. And then the other thing is, if we have the column here, basically our strut over here is roughly equivalent to the area of the column. And whenever you're checking a strut, it can have different dimension at the top and at the bottom. So in this case, we have a smaller dimension at the bottom, a bigger dimension at the top. What's going to happen is we're going to have more like a fan-shaped strut, and our compression forces are going to go from a bigger area to smaller area. But whenever you're checking the strut, you have to use the smaller area, which in this case is half of our pile area because it's limited by the area at the bottom, except if you have a really small column that might govern. So check both and take the smallest area of the strut between the top and the bottom. So that is your area of concrete. And the last thing that you need to incorporate is your efficiency factor. So basically this efficiency factor takes into account the fact that when you have a strut that's perfectly vertical, you can get a full capacity or somewhat very near to full capacity of your concrete. And it also takes into account that if you have a very steep angle of the concrete, like in this angle, the concrete actually starts to fail in splitting. And because of this method of failure, you get a much reduced capacity. And because when it's inclined at a bigger angle, the concrete cannot mobilize as much capacity as it can when it's fully vertical, this efficiency factor reflects that. And if you work it out, it's somewhere between 1 to 0.3. 1 is if it's perfectly vertical, like in this case. 0.3 is the minimum angle that you can have for a strut, which is a 30 degree. So this angle cannot be any more than 30 degree, because if it's any more than 30 degree, it's not really strut and tie anymore, it's going into flexural. So you need to revise your strut and tie model in this case. So that's how we work out our strut design. So let's recap here for a single pile cap how we designed it. First, we sized the depth based on the sufficient length required to develop the bars through the pile cap. And then we've set out our strut and tie models based on minimum eccentricity. We worked out the geometry of that. We knew where is the tie going to be placed and where is our struts. We worked out our angles and we calculated the compression and tension forces of our truss members. Then we checked our struts for compression capacity, and we provided sufficient reinforcement for our ties. And the last thing that we did is we specified the eccentric moments on the pile and we designed it as a column. Now let's jump into a two pile cap where it can start to get a little bit more interesting and complex. So with a two pile cap, what we have here is a slightly bigger, again, strut and tie model. So we have our compressions going from the column into the piles, and we have our tie members at the bottom. This distance here is exactly similar to how we worked it out previously. So you can conservatively assume this is about 100 mil because of your cover. And usually, now this is slightly bigger than when we had it on the top, because on the top you just have the concrete cover above your tie reinforcement, but when you have it at the bottom it's slightly different, because usually they cast the piles in the pile cap, and this amount into the pile cap is usually a 50 mil, and then they place the reinforcement on top of that, which could be about another 50 mil. So overall you end up with 100 mil on the bottom. You can also assume that this is about 50 mil on the top, so you end up with your total depth minus 150. This actually should be a capital D, which is your full depth over here. And another thing is the distance between the reactions. It is the actual physical distance between the piles, but you also have to add eccentricity allowances, because this one might be out and this one might be out. There is a very small statistical chance this is going to happen, but since this is the tolerance, we need to allow for it in our design because it can happen. Now, the first thing we gotta do, as always in any strut and tie model, we gotta work out our external reactions. So we've got our loads coming in from the column. Half of it goes to each pile. That's fairly straightforward because it's equal distance. We know that this is how the reactions are going to be split. From there, we can work out our strut and tie location. We can start working out our angles, and again, based on these, we can calculate our strut forces, our tie forces. We can design our strut, and we can design our tie. One thing is important to note here when it comes to the strut is that with a 2-pile cap, it's usually the column that governs the size of the strut rather than the pile, because previously when we looked at it in our model here, we actually had 2 struts coming out from one pile, and that was governing the strut size here. It's exactly the same here, but it's reversed. So actually this one here is the one that's governing your strut width, and it's usually the one that governs, which is half of your column area. And as you can see here from this 3D sketch, basically your column develops a little bit of its forces, about 50 to 100 mil into the concrete, and then it starts splitting them into one strut here and into one strut there. And basically this area that is shaded over here, that is the size of one strut, and this is basically the size of the other strut. And usually your circular area of the pile is much bigger than the area over here. Yes, the areas don't match. Struts don't have to be perfect. They follow the shape of the bearing element, because that is the shape of your column, that is the shape of the pile. At the top they're gonna follow the shape of the column, and at the bottom they're gonna follow the shape of the pile, and you take the worst one between the two. Don't worry about it being perfect size, because it's not perfect, just the concrete will start diverging the stresses straight away in compression. And as always, remember to size the length of your 2 piles pile cap sufficiently to develop the bars in tension beyond the center of the pile. This distance is really critical, and it usually governs how long your pile caps need to be. Generally speaking, you will need at least 300 from the face of the pile. That is the absolute minimum. Sometimes you'll need bigger than that if you have very heavy bottom bars that need a longer development length. You can always cog your bars to get only half of the development length that you need from the face of the pile. Free pile caps are common as well, and they can often get more complex, but really it is just a matter of applying the load coming in and resolving it into 3 compression forces. Exactly what we did in 2D with the 2 pile groups, you're gonna do it again in 2D, but 3 times on each plane along the piles, and you'll work out your strut forces, you'll work out your tension forces, And from there, it's the same thing. You check your strut capacity, you provide reinforcement for your ties. And that concludes our overview of the pole caps design using strut and tie models to AS3600. I hope you find this helpful. If you do, please subscribe to the channel and keep an eye for future content coming soon.